Chapter 2 Game Feel and Human Perception. Understanding exactly how humans perceive video game worlds we create is key to deciding good game feel. We'll begin by examining our feedback loop model of interactivity from Chapter 1 in great detail. By deconstructing each piece of the system and incorporating the concept of the model human processor, we'll be able to define real time control at the level of specific measurable properties of human perception. This will tell us exactly when and how real-time control can exist and what will cause it to break down. We'll also look at the computer side of things. What exactly are the parameters of machine illusion? Finally, we'll look at some of the limits of perception for game feel. When and how does real-time control exist? In Chapter 1, we defined real-time control as the uninterrupted flow of command from player to game, resulting in precise, continuous control over a moving avatar. It's more like driving a car than having a conversation, as we said. The part of the definition that needs clarifying is uninterrupted. What if the player can offer new input at any time, but the game can only receive it at set intervals? Or what if the player gets locked out for a certain amount of time, unable to add new input until an animation is finished playing? In other words, what is real time control and how do we know when it's happening and when it's not? Let's again look at interactivity, this time with more specificity. There are two halves to this process, the player and the computer. On the player side of things, there are unchanging properties of human perception. For example, there is a minimum amount of time in which a player can perceive the state of the game, think about how to act, and pass that impulse along to his or her muscles. On the computer side, this creates boundaries. To sustain real time control, the computer must display images at a rate greater than 10 per second, the lower boundary for the illusion of motion. The computer must also respond to input within 240 milliseconds, the upper bound for response time. There's also a threshold for continuity. The game must be ready to accept input and provide response at a consistent, ongoing rate of 100 milliseconds or less. If the game responds to input sporadically, the flow of control is broken. The onus for maintaining real time control then is on the computer. The computer's half of the process is changeable, the player's perception is not. Here we have the diagram of 2.1, interactivity in detail. On the player side, the minimum amount of time it takes for a person to perceive the state of the world. Let me reread that. On the player side, the minimum amount it takes for a person to perceive the state of the world, think about what to do and act on the impulse, is around 240 milliseconds. This is a very short amount of time. The correction cycle is the increment at which people make tiny adjustments necessary to assemble a sandwich, drive a car, or exercise real time control over objects in video games. This measure comes from Carrad, Morin, and Newell's model human processor, the collected result of many different studies about human reaction and response time. The figure of 240 milliseconds is an amalgam of three different measurements, one for perceiving, one for thinking, and one for acting. They break down in ranges like so. Perceptual processor, 100 milliseconds, 50 to 200 milliseconds. Cognitive processor, 70 milliseconds, 30 to 100 milliseconds. Or motor processor, 70 milliseconds, 25 to 170 milliseconds. So from senses, there's perceptual, cognitive, which eventually leads to motor, to muscle. What's being measured here is the cycle time of each processor, the time it takes to accept one input and produce one output. The variation comes from physiology and circumstances. Some people have the capacity to process things more quickly than others, and everyone tends to process things more quickly under intense circumstances, displaying a heightened sense of awareness. Likewise, processing speed goes down under relaxed or suboptimal circumstances, such as reading in the dark. In the model, each of the steps is defined as its own separate processor and has its own little cycle time. See figure 2.2 up at the top. Try it yourself. To appreciate the speed at which your processing functions, I highly recommend checking out humanbenchmark.com's reaction time test. This will give you a clear sense of just how small the increments of time we're talking about seem when you're able to measure them against the computer. My best reaction time is about 170 milliseconds. If you're like me, it'll feel a little weird to actually butt up against the limitations of your own perceptions, but there it is. You can't argue with the precision of the computer measuring your reaction time. It's neat that we can measure this. Let me go ahead and see if I can load that up. Just a moment. Got a parenthesis there to take care of. 185 there on the first attempt. Uh, let's try that a little bit again now that I'm a little more familiar with exactly what needs to be done. 247 there. 260 there. 293. 283. Or 289, excuse me. One more time. The red box turns green. Click as quickly as you can. 219. 290. 261. 239. 250 on average. Okay. The idea is that perception, cognition, and action are processed separately but feed into one another, enabling a person to see the state of things, think about how to change them, and then act on that impulse. Know that this is an abstraction of human cognition. Nowhere in the autonomy of the brain is there a structure called the perceptual processor, but it is a useful one because it lets us put hard numbers to components of our diagram. The perceptual processor takes the input from the senses and makes sense of it, looking for patterns, relationships, and generalizations. From all the sensory data, it creates a recognizable state of the world for the cognitive processor. The cognitive processor does the thinking. It compares intended results to the current state of things and decides what to do next. The motor process receives the intended actions and instructions to the muscles to execute it. After the impulse leaves the body as muscle movements, they're out into the wild, woolly reality, and the process starts again with sensory perception. All of this happening in Figure 2.3 at step 2 on our chart of interactivity in the player's mind. Correction cycles and game feel. When all three processors, perceptual, cognitive, and motor, work together in a closed feedback loop, the result is an ongoing correction cycle. A correction cycle happens anytime you do something that requires precise coordination of muscles over time, whether it's picking up a book, driving a car, or controlling something in a video game. Robert Mueller of MIT's User Interface Design Group describes the process. There's an implicit feedback loop here. The effect of the action, either on the position of your body or on the state of the world, can be observed by your senses and used to correct the motion in a continuous process. For example, imagine you want to reach out and grab a muffin that's sitting on your desk. You formulate intent to grab the muffin. As soon as this intent is formulated, it is translated into action of your muscles. Twist trunk and chair, activate arm muscles, open hand into muffin claw, and so on. The moment this action starts, you perceive the precision of your hand in space and see it start to move, responding to your impulses. Uh, the perceptual processor looks at where the hand is in space, passing that information on to the cognitive processor. The cognitive processor thinks about where the hand is relative to where it should be and formulates a new plan to correct that motion. The motor processor then takes the new plan and translates it into action. From the moment the movement starts to when you have the muffin in your hand, you run this continuous process of action, perception, and thought, increasing precision each time as a factor of distance and size of the target. Look at Figure 2.5 there. Intent, grab muffin. Comparison for, and there's the flow for action, perception, reality. There's the correction cycle time. Because we know the cycle time of each processor, perceptual 100 milliseconds, cognitive 70, and motor 70, we know that the time for each of one of these correction cycles, 240 milliseconds. Correction cycles are how people are able to trick and hit targets uh, with precision, steer things, point at things, and navigate the physical world skillfully. To experience this firsthand, check out the example in chapter 2-1. I couldn't find that online. Try putting your cursor directly over the dots as quickly as possible. You see the correction cycle in action as you overshoot, undershoot, and then hone in, eventually coming to rest on your target. Now imagine you're hungry. You're out of muffins, you get in the car, and begin to drive into the muffin store. The overall goal for this trip is to get a sweet, delicious banana muffin. This goal trickles down to different layers of intention, such as turn right on Elk Street at the lowest level. It's about the moment to moment adjustment of the motion of the car to keep in the lane, stop it at red lights, and so on. As before you perceive the state of the world, think about what corrections you need to make to the current motion and make the adjustments happen once every 240 milliseconds. The process is the same as when you're reaching across the desk, except that this correction cycle goes on longer. The muffin on the desk was static and represented a single target, a single intent. Driving to the store might take 20 minutes, fulfilling 20 different sub goals. So the overarching goal would be drive to the muffin store. The intent would be to turn right at Elk Street, or to keep the car in the lane. And then there's the cycle of correction there. In video game, real-time control is an ongoing correction cycle of this type. As with driving a car, control is an ongoing process where their higher order intentions trickle down and become individual moment-to-moment actions. These actions are a part of the ongoing correction cycle. When the player perceives the state of the game world, contemplates it in some way, and formulates an action intended to bring a game state closer to an internalized ideal, figure 2.8, this happens at the same cycle of 240 milliseconds. The difference is, at the point where action normally goes out to physical reality, a video game substitutes a game world for the real world. It hooks right in there. The inputs of the perceptual processor come from the screen, the speakers, and the feel of the controller. The output, instead of acting on objects in the real world directly, act on the controller, which translates the movements of objects in the game world. So here's goal: save the princess. Intent: reach the castle. Intent: stomp the Goomba. There's the cycle of comparison, action, perception. Fitts law. There's a well-known formula, Fitts law, which can accurately predict how quickly you could move your hand to a target of a particular size at a certain distance. Fitts law is an unusually successful and well-studied human-computer interaction model that has been represented and verified across numerous studies. For reference, the formula is mt equals a plus log 2, and then parentheses, and within those is d over 1 plus, or d over w plus 1, where mt equals movement time. So movement time is equal to start-stop time of the device plus speed of the device, with d representing distance from starting point to target, and w being the width of the target measured along the axis of motion. The original formula predicted how long it would take to reach out and touch something of a certain size a certain distance away, as long as it was within arm's length. It was later discovered to be equally applicable to the time it takes to move a mouse cursor to an object of a particular size and shape on a computer screen. So it's applied and studied by using interface designers. For example, the menu bar in the Macintosh OS is always present and takes up the entire top edge of the screen. That means the size of the menu bar is functionally infinite, enabling the user to get the cursor onto it quickly and easily with very few correction cycles. Compare this to a tiny checkbox or a hierarchical submenu. Grab a drink here. Sorry about this. Real-time control relies on the computer sustaining three thresholds over time. One, the impression of motion, displayed above 10 frames per second. The frames displayed on the screen must be above 10 per second to maintain the impression of motion. The impression will be better and smoother at 20 or 30 frames per second. Instantaneous response, input to display happens in 240 milliseconds or less. The computer's half of the process must take less than the correction cycle for the player. At 50 milliseconds, the response feels instantaneous. Above 100 milliseconds, the lag is noticeable but ignorable. At 200 milliseconds, the response feels sluggish. Continuity of response, a cycle for the computer's half of the process stays at a consistent 100 milliseconds or fewer. The impression of motion. Similar to film and animation, the way we compute that computers create and sustain the impression of motion is well understood. Think of each cycle of the player's perceptual process as a snapshot of reality, incorporating visual, oral, tactile, and proprioceptive sensations. Each 100 millisecond cycle, the perceptual processor grabs a frame of all the stimuli. If two events happen at the same frame, Mario in one position, then Mario slightly to the left, they will appear fused as a single object in motion rather than a series of static images. Figure 2.9. This is perceptual fusion. From the computer side of things, perceptual fusion explains how objects in a game appear to move. The display is updated 10 times per second, 100 millisecond cycles equals 10 frames per second. This is sufficient for the illusion of motion. This is right at the border through, and it won't feel very good. 20 frames per second is better, and 30 FPS is where motion begins to be pleasingly smooth. Most game runs at most games run at 30 FPS or higher for this reason. As game developers know, with frame rates that vary based on processing power used, it's better to be safe than sorry. There's no such thing as a frame rate too high. Instantaneous response. Perceptual fusion also influences the impression of causality. If I flip a light switch and the light comes on within the same perceptual cycle, I will register this as a cause and effect relationship. My action caused the light to turn on. The same thing is true for computer response. If I move a mouse and the cursor seems to react immediately, I tend to assume that the effect was caused by my action. An extension of this impression of responsiveness. Professor Miller describes the process. Perceptual fusion also gives an upper bound on good computer response time. If a computer responds to a user's action within 100 milliseconds, its response times feels instantaneous with the action itself. Uh, Systems with that kind of response time tend to feel like extension of the user's body. With reality, there's never a problem with lag. Now, response will always be instantaneous. In a game, response will never be instantaneous. Even a game running at 60 frames per second, a 3-frame delay is all but inevitable. 3 frames at 60 frames per second means 50 milliseconds. You can convert frames per second to milliseconds if you divide by 60 and multiply by 1000. So 3 frames at 60 FPS is 3 divided by 6 times 1000 equals 50 milliseconds. Mick West, programmer and designer of the original Tony Hawk mechanic, defines this as response lag. Response lag is the delay between the player triggering an event and the player getting feedback, usually visual, that the event has occurred. If the delay is too late, then the game will feel unresponsive. Here's a little graph of response time and player perception. So between 0 and 100, things can be perceived as instant, and between 150 to 200 or more, things are sluggish. Over 240, real time is broken. Mick West on responsive. Check out Mick West's articles about programming for responsiveness at www.cowboyprogramming.com. He offers an awesome technical grounding for avoiding response lag as well as a engagingly practical way to measure response time in any game using an inexpensive digital camera, recording both screen and controller at 60 FPS. There's no exact point at which a game's response lag can be said definitively to have gone from tight to sluggish, because other factors, such as mapping and polished effects, can shape this impression of responsiveness. But there is a threshold above which the sensation of real-time control is broken, 240 milliseconds. Past this response time, the player can perceive, think, and act before the computer is ready to accept a new input. If it takes a player 240 milliseconds to perceive, think, and act, how is it that the computer has to finish its tasks and offer feedback within 100 milliseconds for the response to seem instantaneous? This is because all the human processors run concurrently. The perceptual processor passes information along the cognitive processor, then starts cycling again. By the time the instructions from that original cycle have been sent out into the world as movements of the muscles, 3 perceptual frames have passed. In real life, this never matters because the response is always instantaneous. When the motor impulses passes to a game, though, there will always be some lag. And here we can see a diagram showing the concurrency of the running processes. What this means is that the game needs to update faster than the player's perceptual processor is running. If it doesn't, the feedback from the game will skip perceptual frames and the player will be aware of the lag. The game has to enable input at any time, even though the player won't be giving it all the time. This enables the player to modulate an input over time, adjusting it incrementally. The steering wheel will remain pulled to the left, and the car will continue steering to the left, even though the player adjusts how much it's turning at 240 millisecond intervals. This is the threshold of continuity. The computer half of the process must update consistently or below 100 milliseconds for real-time control to be sustained. Continuity is tricky to measure. Many games respond to input at some times and not others. This can be a frame rate drop, a delay between the computer and the display, or a problem with the processor being overloaded by too much awesomeness in the game, not being able to pass frame along to a display in a timely manner. Anytime the computer's half of the process takes more than a cycle of the perceptual processor, the player will notice. If it takes more than a correctional cycle, real-time control is broken. Other times, however, the delay is part of the game. For example, if I execute a fierce punch with Zangief in Street Fighter 2, I lose control of the character for about 750 milliseconds. This is longer than the threshold needed for the ongoing correction cycle by 510 milliseconds. The temporary loss of control is ignorable, though, because I chose when to trigger that move. It becomes a risk-reward trade-off rather than a disruption. It also makes sense in the context of the game's unique world. Big dude, heavy punch, does a lot of damage. It should take a long time to execute. I knew what I was getting into. This shows that the continuity of real-time control can be broken without interrupting the player's feeling of being in control. This makes interruption more than simply a response time too long or broken continuity. It means interruption can be smoothed over by other factors, such as metaphorical representation. Real-time control, then, is a gestalt. It primarily relies on the computer sustaining three thresholds over time: the impression of motion, instantaneous response, and continuity of response. But the ultimate judge is the player. The designer may have done something clever with the input mappings or animations to mask any interruptions to the flow of control. The end result is an impression in the player's mind. If it feels like real-time control, it is. Now let's explore perception and game feel implications for game design from a more general point of view. Let me grab a drink. Some implications of perception for game feel. To examine game feel is to see perception in a particular way. First, game feel includes many senses: visual, tactile, oral, proprioceptive. Experiencing game feel, these senses combine into one sensation. Second, the notion of prescribed embodiment should be addressed. Game feel also enables objects externally to the body to be subsumed into the body image and feel like extensions of the body. Third, game feel is an ongoing process of skill and building and practice. It is part of the larger realm of human skill building and relates to the skills like driving and playing tennis because it requires the same kind of repetitive practice to master, from noob to elite, as it were. Lastly, a model for perception for game feel needs to encompass the physical nature of game feel. Experiencing game feel is like interacting with a surrogate reality which obeys its own rules, which must be understood through interaction and observation. Expanding on the experiences in Chapter 1, here are 5 interesting ideas about perception that support our definition of game feel. Perception requires action. 1. 2. Perception is skill. 3. Perception include thoughts, dreams, generalizations, and misconceptions. 4. Perception is a whole body experience. 5. Tools become extensions of our bodies. Perception requires action. In order to perceive something, you have to see it in action. This has been verified experimentally with kittens and blind people. The kitten study, held in Hein, 1963, involved 2 groups of kittens, each raised in the dark. The first group was allowed to roam freely, while the second group was kept passive, which we can only reasonably assume meant a Clockwork Orange style tie down. The experiments controlled the conditions such that both groups of kittens were exposed to the same limited stimulus, flickering lights, sounds, and so on. Then they released the kittens into a normal, lit environment. The ones who had been allowed to move around in the dark were able to function just fine, while the ones who were tied down helplessly staggered around as though blind. While this seems to indicate that perception is an active rather than passive process, the lights and images used to stimulate the kittens didn't make much difference. Being able to explore their surroundings and perceive things and motions relative to their own bodies did. To perceive, you need to interact. Another study, Bach Y. Rita, 1972, did something similar with a bunch of blind folk. The researcher created a special video camera driven matrix of stimulation points shown in figure 213. Let's take a peek at that. Alright. A TV camera mounted on spectacle frames sends signals through electronic circuitry in an array of small vibrators, left hand, strapped to the subject's skin. The pattern of tactile stimulation corresponds roughly to an enlarged visual image. Each vibrator was mapped to a particular pixel of the image that the video camera was receiving, giving a sort of tactile image of what the video camera saw. When the perceptions were allowed to move, the cameras themselves, they were able to learn to see in a limited way. If they were not allowed to control what they were looking at, the image stimulus devices were just gentle, if unskilled, masseuses. The concept, the concept that perception requires action has relevance to game feel because it accurately describes the sensation of exploring and learning your way around an unfamiliar game space, and it correlates physical reality with virtual reality in a meaningful way. The things you're controlling in the game becomes your surrogate body, your hands. Humans are adept at learning the physical properties of new and unfamiliar object and do it very quickly. Noodle it around in your hands and you soak up a wealth of detail, weight, density, material, texture, color, so on. The same ability extends to virtual objects and, interestingly, to virtual worlds governed by different rules, laws, and physics. For some reason, it's immensely pleasurable to suss out a new and unfamiliar world by probing around in it and using a virtual instrument. The thing being controlled becomes both expressive and perceptual. As you control it and move it around, feedback flows back through it to your eyes, ears, and fingers. Perception is skill. If perception requires action, that action must be learned. We don't usually think of it this way, but perception is in some ways just a set of skills honed across one's lifetime. From the moment we're born, we learn new distinctions, forge new neural pathways, and generally undertake an ongoing process of becoming better at perceiving. Grab keys, insert keys in mouth, rinse, repeat, and learn. So it goes until a fully functional adult emerges. Perception is to a large extent an acquired bodily skill that is shaped by all our interactions with the world. As Dags Vani says, part of this process is making generalizations and learning abstract concepts like justice, freedom, and cheesecake. Another part is bringing with us all experiences that come before. There's a concept from two venerable psychologists, Donald Snink and Arthur Combs, that vividly portrays the role past experiences, ideas, generalizations, and fantasies play in perception. The perceptual field. Uh, Near as I can tell, the idea started with Singh and Combs in 1951 as the phenomenal field. Combs changed the phenomenal field to a perceptual field in a later work, so we'll stick with that. I prefer that anyway, as it's more descriptive of the concept as it applies to game feel. Just a moment. People have a great deal of practice navigating the space around them and developing relationships with the things in that space. Singh and Combs captured the phenomenon of memory, perception, and skill, building with the concept of the perceptual field. The idea of a perceptual field is that perceptions carried out against the backdrop of all previous experience, including our attitudes, thoughts, ideas, fantasies, and even misconceptions. That is, we don't perceive things separately from what's come before. Rather, we experience everything through the filter, against the background, and within the structure of our own personal vision of the world. Another way to put it is one's constructed representation of objective reality. The meaning given to the profusion of stimuli that bombarded the brain are organized and conceptualized on the basis of individual and personal prior experiences. And still one more way. The perceptual field is our subjective reality. The world uh, are aware of, including physical objects and people, and our behaviors, thoughts, images, fantasies, feelings, and ideas like justice, freedom, equality, and so on. So your perceptual field is your word, your structural understanding of everything you perceive around you and its meaning. This is a cool idea because it goes a bit beyond the notion of simple mental model, which is more about dry, clinical details of how a person thinks a thing functions, usually compared to the system image, the way the thing actually functions. In the case of a video game, the brain recognizes that the world of the game is a subdomain, a microcosm of the larger perceptual field of reality that it understands. It's appropriated, separate, and obeys its own rules. At the same time, the mind brings all of its past stored experiences to the table to help it understand this new place. The difference is that a game world is not necessarily governed by the rules of physical reality or bound by them. This is a separate, useful way to think about the creation of game feel as the creation of a separate but related physical world, simplified but whole, cohesive, and self contained. Many times, creating and tweaking a game feel system means literally the construction of a set of generalized laws and rules that govern all action within the system. It's like writing your own universe from scratch. You have your own gravity, your own simple momentum and friction, your own simplified definition for what collision between two objects means, and how it should be resolved. The world around you is objective and immutable. You're not going to wake up one morning and discover that gravity has suddenly stopped working as expected. I throw a grapefruit at a wall, it's going to hit the wall with a thud and fall to the ground. This kind of consistency can be frustratingly difficult to achieve in a game world. Because the way we cope with and understand events in the game world is so similar to the way we interact with the real world, we expect the same consistency. The tiniest thing can break this perceptual immersion. Unlike a film, which represents one frame perspective on a world that has only to maintain visual and oral consistency within that frame, a game has to stand up to active perception. The player can freely explore every possible permutation of every action and response in the entire world. This is the skill of perception, the one every human being has been constantly honing before birth. Because people are extremely skillful at perceiving the world around them, any tiny inconsistencies become glaring and obvious. A character's foot clipping through a stair on an invisible wall, these things never happen in the world around us. So this process of discovery is much closer to our experience of being in the world than the experience of passively viewing a film or reading a book. The same mechanisms we use to cope with the world around us, to understand it and function within it, come into play when exploring a game world. It is the same process of expanding the perceptual field into this new world and pumping around it to make generalizations and distinctions needed to interact with and succeed in the world. This is why a consistent abstraction is so much more important than a detailed one. It's fine to create a simplified version of reality for players to interact with. They'll figure out the parameters of the world, its constraints, rules, and laws of physics within minutes of picking up the controller. Just don't violate the rules yourself have set. If an object is portrayed as being large, heavy, and massive, don't let it go flying off into space with the slightest touch, or pass through another object without interaction. Easier said than done, of course, but this is the same level of but this is at some level a designer's decision. Excuse me. Better to have a simple, tight, cohesive world like Dig Dug than a weird, inconsistent one like Jurassic Park Trespasser. People are going to figure out everything about your world either way. Our physical reality is much more complex and nuanced than any game world, as we've got years of experience at perceiving it. Better to make it simple and self-consistent than a broad, incoherent mess. Um, Perception is as a skill is also correlated to the way people get better at things over time. You practice something, you get better at it. Your perceptual field includes an ever growing body of experience about the task, which makes each new try at the task easier. It's not just a bank of information to draw on, but affects what happens at the moment to moment level of perception and action. Chris Crawford would say that the neural pathways are getting pushed farther and farther down, away from the conscious processing into subconscious automatic processing. Merleau-Ponty defines the distinction as abstract versus concrete movements. If an action is unpracticed and requires conscious thought and effort, it's an abstract movement. It's also if it's so practiced that it happens automatically and without conscious thought, a pure translation of intent into action, then it's considered a concrete movement. By this process, people learn things incrementally over time, turning what was once difficult and requiring deep conscious involvement into an easy and subconscious action. Clearly, this is what happens with game feel, though the process is almost always much quicker when learning a game skill. However we conceptualize it, it is obvious that humans get better at skills they practice. And if we consider all perception to be skill, this handedly explains why games feel like such a skill-driven activity, why skill learning is the price of admission to experience it. Perception in the game world is just a simplified, modified version of perception in the real world. The rules are different, but the process is the same. Perceptions include thoughts, dreams, generalizations, and misconceptions. Just a moment, guys. All right, let's get back to it. Another interesting offshoot of the concept of the perceptual field is that it echa hmm. Oh, excuse me. Another interesting offset of the concept of perceptual field is that it encompasses not only physical reality, but attitudes and ideas. Perception of something is heavily influenced by biases, ideas, generalizations, and worldview, all of which have become incorporated into the perceptual field through a lifetime of experiences. Of course, generalizations about a particular thing may not accurately reflect the objective reality for that thing. For example, I have a central heating and air conditioning system in my apartment. One day I was cold and wanted to adjust the temperature. The wall mounted control unit displays the current temperature based on the thermometer, which is somewhere in the apartment, I hope, I think. The current temperature is compared to a sliding blue control representing the desired temperature. I assume that if I move the sliding control to a temperature different from the actual temperature, the air will turn on and will adjust the temperature. The current temperature reads 61 degrees. I move the control from 63 to 75. The cold air turns on briefly and then turns off. Excuse me. A few minutes later, the air turns on for a longer period, blowing warmer air, and then turns off. Eventually, I get fed up and turn the temperature to 90. Again, the air turns on for a few minutes, warm, and then turns off. I get a blanket, and an hour and a half later, I walk into my office, the door of which has been closed, and I'm suddenly sweltering hot and realize I've left the temperature on at 90. I toss the blanket, strip down to a t-shirt, and check the thermostat, which now reads 77. I put the thermostat back down to 72. The air turns on for a few minutes, cold, and turns off. Gah. What's going on here? In my conceptual model of the heating system, there's a certain threshold between the actual and desired temperature. If that threshold is exceeded, the desired temperature is 3 degrees above or below the actual. For example, if the system turns on and applies an amount of heat or cold equal to the change in temperature that's necessary to bring actual back in line with desired. Let me reread that. For example, the system turns on and applies an amount of heat or cold equal to the change in temperature that's not necessary to bring actual back in line with desired. The reality of the system is that it turns on and blows air, either hot or cold, for a certain duration. 5 minutes of hot or 5 minutes of cold, depending on which way the temperature is supposed to go. The hot isn't particularly hot, and the cold isn't particularly cold, but applied across a long enough time scale, they get the job done. In addition, the timer that governs how long each on state should last functions independent of the controls. That is, always counting down 5 minutes at a time. If you switch the heat on with 30 seconds remaining on its 5 minute cycle, you get 30 seconds of cold air because it takes a while for the heater to warm up. And there are only 30 seconds of on remaining before the system goes back to the off state. Oh, and the thermostat evidently is in the office. All right, we're on page 53. Donald Norman would say that my mental model is out of sync with the system image of the heating system. I hold in my mind a logical construct, a picture of how the system works, but that picture is wrong. The construct frames my interactions with the system and dictates my expectations about what the system will be for a particular input. If my mental model differs from the system image, the way the system actually functions, errors occur. Norman would say that the designer's fault and go on to point out that the design model, the way the designer imagined the user would interpret the system, is out of sync with the user's mental model. This is definitely applicable to game feel as it helps greatly in distinguishing what players feel or what or excuse me. It helps greatly in deciding what players refer to as intuitive controls. Norman suggests seeking out and exploiting natural mapping between input device and system. For example, in Figure 214, stove C makes more sense than stove A and B, uh, than stoves A and B, and is far easier to operate because there is clear spatial relationship between the position of the knobs and the position of the burners they operate. Finding natural mappings in game is a similar process, though not always an obvious one. So here we could see a few models. Three configurations offer three different correlations between stove burners and controls. Yeah, stove C definitely makes the most sense to me there. I like the example of the game Geometry Wars, which tends to be easy for people to pick up and play effectively. The movement of the thumbstick corresponds very obviously to the motion of the little ship in the game, making this something of a natural mapping, albeit one in a virtual space. Figure 215. The motion of the thumbstick in Geometry Wars offers a simple and clear connection to the action taken by the ship. The only problem with Norman's concept of the mental model is its rigidity. To to say I have a mental model of the world of The Legend of Zelda The Wind Waker could be useful to isolate and tune certain mechanics to eliminate ambiguities and make the controls more intuitive. But it ignores the fact that I have a relationship to that world. I feel a certain way about it and think a certain way about it. And breaking that down into dry, clinical logic diagrams seems to ignore some of the most important parts of the relationship. Some of the parts of the designers understood and worked really hard to develop. For example, it's extremely important to the success of the game that I feel a sense of freedom and adventure while sailing the open seas in the game. I could distill that to a system image of many possible actions while sailing, but that would miss much of the point. It's not as important to track exactly how far objects are spaced apart, or how far I can sail in one direction before hitting something, or how long it takes to get from one object to object, as it is to make the space of that world feel open, free, and full of possibility. I can sail aimlessly in a particular direction and be certain of two things. One, I'll be free to sail as far as I want in that direction, and two, eventually I'll find something new and interesting. The system, speed of the ship, sharpness of turning, distance between islands, and so on, what would be interesting to track, as would a player's mental model of that system. But it definitely misses one of the essential experimental qualities of the game. A few small changes to the system, making the ship move 20% slower, for example, could make the oceans of Wind Waker feel impossibly large, tedious, or lonely. The idea of a perceptual field that incorporates not only the system image, but the thoughts, ideas, feelings, and generalizations about the system that players have brought with them, and is consistently forming and reforming, is much more effective for understanding that experience. Another important thing that Norman's mental model concept ignores is paradigm shifts, aha moments, as master puzzle designer Scott Kim would say. For example, another Zelda game I've been playing recently is The Legend of Zelda Phantom Hourglass for the Nintendo DS. In that game, there's a particular puzzle that requires players to expand their perceptual field. In one particular part of one temple, players are told to step up to the altar and stamp their map at the location of a new area to be explored later. At first, this puzzle threw me for a loop. To access new areas in The Legend of Zelda Phantom Hourglass, you first need a sea chart for that area. The new location can be stamped is outside of your current available areas, but clearly corresponds to the map you've had access to and used throughout the game. I systematically exhausted each possible action I'd ever used in the game, and then some I'd only excuse me, and then some I'd only ever used in other games. I pressed buttons, scrubbed the stylus back and forth in every conceivable pattern. I drew X's and O's, traced the pattern of the Triforce over and over again. Nothing in my perceptual field equipped me to deal with this puzzle. Clearly, my current understanding of this system is inadequate and flawed somehow. I had to take a step back and reflect on my perceptual field. So I started thinking about other possible interpretations of stamping, and the other possible ways I might stamp this stupid map, short of putting the DS on the floor and stamping it with my foot. The solution eventually occurred to me. Close and open the DS quickly. It's sort of a stamping motion you can see in Figure 216. The problem was my perceptual field. My combined understanding of the DS, how the DS functioned, and the possible actions in the game. There was no reference point for using the functional opening and closing of the DS as an action in the game. Across all my experiences with playing DS games, which are numerous, I had never come across a game that used the function closing and opening of the DS lid as a button. New Super Mario Bros. Says goodbye in Mario's voice if you close the lid of the DS while the game is still on. But that was my only point of reference, my only hint in the entirety of my perceptual field. I solved the puzzle through a paradigm shift by seeing the system in a new and different way. I felt a rush of pleasure and enjoyment as I incorporated this new information about the very nature of the game's universe into my perceptual field. I had amended and changed my mental model not only of this particular game, but all games I'll ever play on my DS in the future. Um, this was not an error or breakdown in my ability to interact with the system, but the point of the puzzle, and in some sense, the whole game. So what's going on here? I was rewarded with pleasure by expanding my perceptual field. Uh, Norman's mental model would call this an error, blaming the designer for misleading the player. Since this is one of the fundamental pleasures of playing this game, clearly something's missing. The perceptual field gives us a way to understand that game as much as the perceptual field gives us a way to understand that game feel is much about how players feel about a particular space and their relationship with it as it is about the dry clinical details of the mental model of that space they keep in their minds to help them deal with and understand events in that game world. The dry details are important. They represent the player's understanding of the physics and rules of the game world and are a great way to find dissonance that causes player confusion. But they are not everything. Perception is a whole body experience. Eyes, ears, tactile sense, proprioception. There is no separation when a person perceives something. Just a moment. For example, a fork. It's shiny and has a pointed end. It's cold, hard, and solid, but easy to pick up. I can eat food with it. It sinks in water. My ideas and perceptions are about what the object is, how it behaves, and what it means, combining to the concept of fork. This is my attitude towards forks and generalizations I can apply later to other fork like objects. The subconscious nature of perception makes a complex process, one which involves all senses and which constantly and rapidly brings us closer to the world we inhabit. The takeaway here is not to think of each kind of stimulus as somehow separate, but as an integrated part of perception. This is how a combination of visual sounds, proprioceptive sensations, from the positions of the fingers on the controller or whatever, and tactile sensation, from controller rumble or haptic feedback, become a single experience in a game. A game world substitutes its own stimuli for those normally created by interacting with the real world, but the experience of perception is much the same. This also indicates why we're so sensitive to inconsistencies between stimuli. If a large hulking mass of a character steps through a staircase or has their arm pass through a wall, the brain says, hey, that's not right. The experience of perception of real life phenomena never has inconsistencies across stimuli, so the brain has a hard time ignoring them when they happen in a video game. Tools become extensions of our bodies. As we said in Chapter 1, a tool, once picked up, is an extension of the senses. It's used for both action and perception. Intent and action can be expressed through the tool as though it was part of the body, and feedback flows back through it. Another way to visualize this is to think about a blind man's cane. When the blind man first starts using a cane, it's unfamiliar and requires a lot of reflection. The tapping movements are unpracticed, abstract movements to him. As he gradually builds skill at perceiving the world through the cane, he's able to more accurately and effortlessly tap around, getting a clearer read on the surroundings. His intent begins to flow effortlessly from the cane. Any barrier between him and the cane is removed, and the cane becomes an integrated part of his perceptual field. The cane now acts just as his hand would. It probes around, touching things, interacting with the world around him, and returning him crucial orienting feedback. This helps him establish a much larger personal space, and also something called the perceptual self. Quite literally, his perceptual field has been extended to a much larger physical area around him. Effectively, he's made his arm's reach much greater. We might say that by integrating the tool of the cane, he's changed his world. So, what does the blind man and his cane of reaching +3 teach us about the game feel? One interesting distinction is between body space and external space. When we interact with the world, we perceive our bodies in two ways: as part of ourself and as one object among the many objects of the external objective world. As Dags Vanese puts it, the bodily space is different than the external space in that it exists only as long as there are degrees of freedom and a skillful use of freedom. The body space is mainly perceived by the subject's specific potentials for action. For a totally paralyzed body with no kinesthetic experiences, there is no bodily space. Different bodies given rise to different spaces, and so do external factors such as clothing, tool use, and different kinds of prosthesis. It's important to notice that learning a new skill also changes the body space. The idea that bodily space is defined by the potential actions of one's body in the world correlates very clearly to the way players interact with game worlds. Players tend to think in terms of abilities and constraints within the game world. It is possible and often desirable to create a game where abilities change across time, where the player itself has different tools that change across time as well. For example, if I'm playing a Samus Aran, my abilities, my bodily space Samus, within the game world of Metroid, are defined by the abilities currently available to me. I may or may not have the Morph Ball. If I do, I can transform into a small rolling sphere and exploit tiny corridors. The very nature of the world has changed, as has my potential to interact with it. The objective world of Metroid is the same as it ever was. Every block is still in the same position as it was before. My abilities, my verbs, my virtual bodily space have changed the world. The interesting thing about thinking is that it does not consider Samus Aran a tool. To say that we can incorporate a tool into our bodies, and that the tool can become an organ of expression and perception, and that our identity and perceptual field subsume is useful, doesn't quite define what happens when a player takes control of an avatar in game. I want to call Samus Aran a tool, not just because she has an identity as a freestanding character that I'm temporarily inhabiting and controlling, but also because she has her own bodily space. She has her own tools which can become part of the body and extend her own perceptual space. In this way, a video game world is truly a micro world, and perception within this micro world is a surrogate for real world perception. It's an interesting idea, it seems, to explain why identity in a video game is so very malleable. It can go from being Gordon Freeman one moment to cursing his vile cleanliness the next. This is because the constricted subdomain of a video game reality provides two other kinds of spaces: virtual bodily space and virtual external space. A video game has its own model of reality, internal to itself and separate from the player's external reality. The player's bodily space and the avatar's bodily space. The avatar's bodily space, the potential actions of the avatar in the game world, is the only way in which the reality of the external reality of the game world can be perceived. As in the real world, perception requires action. The difference is that the action in the game world can only be explored through virtual bodily space of the avatars. Players extend their perceptual field into the game, encompassing the available actions of the avatar. The feedback loop of perception and action that enables you to navigate the world around you is now one step removed. Instead of perceiving primarily through interactions of your own body with the external world, you're perceiving the game world through interaction of the avatar. The entire perceptual apparatus has been extended into the game world. To wrap back to our earlier discussions of identity and game feel, how does this concept of avatar as perceptual substitute rather than extending tool relate to proxied embodiment? Because a game world represents its own reality external to its avatar's bodily space in the same way that the physical world is external to our own bodily space, it seems much more like substitution than an extension. The same game world, the same might be said for identity. We said that objects outside ourselves, objects in a game world, can become extensions of identity. Vessels for identity might be more accurate. The view of tool as extension of body defines the self is in terms of perception. The perceptual self is the immediate surrounding environment and your ability to interact with it, your potential for action. To say he hit me instead of he hit my car, or his car hit my car. It's an artifact of the way we perceive the immediate environment around us and the fact that an inanimate object can become a part of the perceptual self, part of the perceptual field. You literally perceive the world through the car as you actively control it. Again, the way we perceive feels game feel seems to be much more of a substitute than an extension. I perceive the world of Hyrule as Link via his virtual body space. My identity intermingles with Link's as I take over and make my own his skills and ability, his bodily space. So, in summary, where and when does real-time control exist? On the human side of the equation, we categorize three types of processes: perceptual, cognitive, and motor, which work together in a closed feedback loop. This feedback loop results in an ongoing correction cycle. In a video game, at the point where action normally goes out to physical reality, the designer substitutes a game world for the real world. This reinforces the idea from Chapter 1 that game feel is an experience of a unique physical reality. On the computer side, real-time control relies on sustaining three time thresholds: the impression of motor, perceived instantaneous response time, and continuity of response. Knowing the duration of the human correction cycle and the relationships between the three human information processors, we can say with certainty that a particular game has or does not have real-time control. The known variable here is the player perception. In the end, game feel is an impression in the player's mind, examining the frame rate, response time, and continuity of response in a game, and comparing this to the threshold of 10 FPS for motion, 240 milliseconds for control, and 100 milliseconds for continuity, gives us a baseline and is useful for classification. But motion at 10 FPS feels stilted, and at 200 milliseconds, response time feels sluggish. These impressions can be smoothed over by use of gestural input by playing back animations. In the end, the player's perception is what's important. The ultimate goal for game feel is to create an impression in the game's mind. Finally, we looked at some other implications of human perception. Perception requires action. Perception is whole body phenomenon. Perception is an effortless fusion of visual, oral, tactile, and proprioceptive stimulus. Perception is an ongoing process of skill building. Perception can be extended to tools. These explain, in terms of human perception, the experiences outlined in Chapter 1. Understanding how human perception works offers us insight about the imperfect apparatus of human perception that we're designing for, knowing that this will help us to develop a palette of game feel that's separate from the emulation of reality and doesn't borrow from film or animation except where applicable. If we understand how perception works, we can build games that feel good instead of trying to build games that feel like things that feel good. Alright, 60 pages in. Tune in next time for Chapter 3, the game feel model of interactivity.